So, we saw the following last class, we saw the parity quantifier. Okay. And we saw some properties of this quantifier, namely that parity of two formulas, parity phi and parity psi is equivalent to parity of this formula phi dot, right, phi dot xi. Okay, so, we saw how to define this new formula based on the two, and these two are equivalent. So, similarly, parity of phi or parity xi is equivalent to parity of phi plus 1 dot xi plus 1 plus 1. Okay. So, this plus 1 is nothing, but you just have a trivial formula which has only one satisfying assignment, and you look at the sum of that with phi or xi, whatever it is. And thirdly, not parity of phi is equivalent to parity of phi plus 1. Okay. So, this shows that the class, let us say parity P, or any for any complexity class C, if I equivalently define a class parity C. Okay. So, we will see how to define that, but for the time being let us only bother about parity P. So, this shows that parity P is closed under complement. Okay. So, in other words, we can without loss of any generality talk about a parity P machine which accepts if there are an even number of satisfying assignments, okay, because I can always add one extra assignment to get a new formula. Okay. So, what do we have? So, the idea, as I said last time, was to amplify the parity sat version of Vaillant-Vazirani, right. So, that was the idea. So, let us write down what we want to do. So, the theorem is, okay, so given any polynomial q, there exists a probabilistic machine M such that given a formula phi over n variables, if phi is satisfiable, then the probability that, so basically what this machine does is that it takes the formula and it outputs another formula, okay, in the same manner as Vaillant-Vazirani, but we will see it slightly different. So, M phi will output another formula which belongs to parity sat with very high probability 1 minus 1 over 2 to the power this q n. So, whatever polynomial we want, we can boost up our success probability to that much. Okay. So, this is greater than, and if phi does not belong to SAT, then yeah, I can just write this as m phi also does not belong to SAT. So, it is not satisfiable with probability 1. So, yeah, so the idea is very simple. So, what do we do? So, what does the corollary of Vaillant-Vazirani give us? So, the actual version of Vaillant-Vazirani said that there exists a probabilistic machine which, given any formula, if that formula is satisfiable, M will output another formula which has a unique satisfying assignment, right. And if phi were not satisfiable, then this has no satisfying assignment. In other words, if it has a unique satisfying assignment, I can consider that to be as a instance of parity set with probability 1 over A10, okay, with success probability. So, now I want to boost that 1 over A10 to 1 minus 1 over 2 to the power q n for any q. So, the idea is again basically to take t trials. Okay. So, I want to take some polynomially many trials of that earlier machine. Okay. So, the proof is, so let m prime be the machine of Vaillant-Vazirani from last class. Okay. So, we construct our machine M as follows. So, run M t equal to some number of times. So, we will see what that t is. Okay. And for each iteration, let psi I be the formula given by sorry, this is m prime given by m prime. Okay. So, we have some t formulas, and what do we know? So, we know that okay, so now construct a formula xi which is the OR of no. So, I want to construct a formula xi such that this is odd if and only if I take the OR of all these parities psi I, that is odd. Okay. So, I will construct a phi in this manner, and the reason why I construct such a phi is because of property 2. Okay. I mean, I have all these individual xi's and I am taking a OR of them. So, I can always construct a another formula xi whose parity is equivalent to the OR of the parity of all these ORs. Okay. And not only that, the other property that we have is that if the initial formula, if phi was not satisfiable, then all these psi i's are also not satisfiable. So, no matter how many ORs we take, it will always be 0. Okay. So, by property 2, this can be done. So, now what do we want our t to be? So, basically what is the probability of error here? Okay, so, phi is in SAT implies that the probability that this psi that we construct, so suppose this is not an instance of parity set, how much is the probability of that happening? So, this does not belong to parity set if none of these belong to parity set, and what is the probability that none of these would belong to parity set? 1 minus 1 over 8n, right, for each one of them, because their success probability is 1 over 8n. So, failure probability is 1 minus 1 over 8n. So, the probability that this happens is less than 1 minus 1 over 8n whole to the power t. Okay. So, in other words, the probability that psi would belong to parity set is 1 minus is greater than or equal to 1 minus this quantity. And if phi is not satisfiable, then by what I said earlier, this is also not satisfiable by our construction. So, now we can very easily see what t we want. So, we want a t such that it must be greater than that quantity. So, in other words, the failure probability should be less than this quantity. So, we want a t such that 1 minus 1 over 8n to the power t should be less than 2 to the power minus q of n, where q is a polynomial. So, I think taking t like something like n times q of n will work. Okay. So, if we fix to t to be n dot q of n, or maybe some constant times n dot q of n, let us say maybe 10 or something, 10 n q of n, that should satisfy this inequality. Okay. So, yeah, so this is still fine. So, this is still a polynomial. So, yeah, so this is a standard way of boosting the probability of any algorithm which has one sided error. Okay, so now let us step back a little bit, and so we said earlier that we will look at several applications of this Valiant-Vazirani theorem. So, one application we saw last time where under certain conditions we got an RP algorithm for any problem in NP. So, there is also a very famous application, and this is popularly known as Toda's theorem. Okay. So, this was proven in 91, and this is actually a Gödel Prize winning work. So, Gödel Prize is one of the top prizes in theoretical computer science, and due to this work of Toda, in 98 he got the Gödel Prize. So, we will look at this proof maybe in the next couple of lectures. So, what he showed was that the polynomial hierarchy is contained in p to the sharp p. Okay. So, you have a polynomial time machine which has oracle access to a sharp p function, and not only does it access this oracle, it accesses this oracle only once. Okay. So, during the suppose you are given any problem in PH, the polynomial time machine during its execution it computes just one let us say a sharp SAT instance. So, let us say it creates some Boolean formula, and it asks the oracle how many satisfying assignments does it have. So, based on whatever answer the oracle gives, it continues its deterministic computation and is able to solve the pH problem. So, this is quite strong actually, because so if you recall, so why is this important? So, Sharpie I defined it last time, no? Okay. So, Sharpie is okay. So, let me define it. So, Sharpie I think I defined it last time. So, it is the class of functions f. Okay. Okay. Let me define it this way. So, we say that so let us say we have a function some 0 1 star to n. Okay. So, this belongs to Sharpie. So, this is a function class, this is not a language in the traditional sense. If there exist right. So, what was the definition? Did I give a definition based on NP or just a number of certificates of a number of certificates? Yeah. So, there exists some polynomial time machine M, right. Yeah. Okay. So, let me just complete it anyway. Polytime machine M such that for all x, it is the cardinality of the number of y's such that x comma y, so M given x comma y accepts. So, for every string x, it is basically the cardinality of the number of certificates that x has for that machine. So, yeah. Okay, so, let us get back to Toda's theorem. So, this is what he had shown. So, what we will do is we will prove this theorem in two parts. So, first we will show that yes. Yes. Yes, a constant number of trials is equivalent to one trial, yes. In fact, even a polynomial number of trials in the case of P, I think even polynomially number of trials can be made equal to one trial, because you are just, well, maybe not, yeah, it will probably depend where it is being called. But yeah, certainly if you have a machine in this class p to the power sharp p, which makes constant number of queries to the sharp p oracle, it can be simulated by another p to the sharp p machine, which only makes one query. I think even log n will suffice, but again I am not sure without a proof. But anyway, okay. So, let us look at some notations and definitions before I begin, and I will then give you the roadmap as to how the proof proceeds. Okay. So, so whenever we talk about L, we will just mean L to be a language, and whenever we talk about script C, we will mean that to be a complexity class. Okay. So, the language there exists L is equal to the set of all strings x such that there exists a string y such that x comma y belongs to L. Okay. So, given a language L, we define this new language there exists L, which is defined this way. So, you can immediately see that NP can be defined as there exist dot P, right. So, there is some machine, so there is some language in P such that there exists a certificate which makes that instance belong to that language. So, this is one way, and similarly, okay, so this is one. So, similarly we define the complexity class there exists C as the set of all languages of the form there exists L, where L is in C, right. Yeah. So, this is how you can define, sorry, this is how you define the one way of defining the complexity class NP. So, NP is nothing but there exist dot P. Huh? No, there exist L is just a language. So, maybe you can say that SAT is there exist dot some language in polynomial time. For example, suppose if you define the following language which given a formula and a satisfying assignment can check if I am sorry, not a satisfying assignment, but given a formula and an assignment checks whether the formula evaluates to true or false on that assignment. So, this is a polynomial time computation. Oh, no, 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 this is not okay, okay, you are saying that as the complexity class, yes. So, there exists L is NL, NL, right. Yeah, but that is a different thing, right. So, but that is not a log space machine. So, if you are looking at the class L and if you are talking about there exists L, it is basically set of all languages of the form there exists dot. So, let me yeah. So, there exists dot, okay, so should not use the word L here, maybe something like L1 or something such that L1 belongs to the complexity class L. Okay. So, here that there exists means that there exists a string such that x comma y would belong to the language L1. Okay. So, since we are looking at the class L, so I would want that string, of course, it has to be polynomially bounded, but so given y. So, of course, it is the class NL, but is NL equal to there exists L. No, that is not, I mean that need not be true, no. Yes, for NP no, that is not true that you can do with a verifier which has log space, because if you take the same problem, let us say the problem where you are given a formula and a assignment and you want to check satisfiability, that is not a log space verifier. Anyway, let us just continue with this and I will try to check that. Okay. So, similarly we can have the for all quantifier. Okay. It is basically the same thing. And for all C is the class of all languages for all L, such that L belongs to C. So, I will define two more quantifiers. So, parity of L is set of all strings x such that the cardinality of the following set y such that x comma y belongs to L is odd. Okay. So, it is a set of all strings x such that the number of certificates that it has is odd, and parity C is parity L for L belonging to C. Okay. So, all these are again traditional languages. We also have the language defined as BP dot L. Okay. So, this is a promise language in the sense that, so BP dot L is defined as its set of yes instances and no instances, okay, where the yes instances are, so what are the yes instances? It is all x's such that the probability over y that x comma y belongs to L is, so what do I want here? Okay, so I will just take the definition of strong BPP for the time being. Okay. So, if necessary we can relax it. So, this is greater than 1 minus 1 over 2 to the power minus q of n, okay, and the no instances are set of all x such that probability x comma y belongs to L is less than 2 to the power minus q n. Okay. And BP dot C is equal to, the language is BP dot L such that L belongs to C. Okay. So, let us look at the way we will proceed with our proof. So, what we will show first is, okay, so Toda's theorem, let me call it 1, is we will show that pH is contained in the class BP dot parity dot P, okay, whatever that means, and secondly we will show that this class BP dot parity dot P is contained in P to the power sharp P. Okay. Yes. So, BP dot L is basically a language whose which is a promise language in some sense. So, basically it has, so if you look at the universe, if you look at sigma star, okay, 0 1 star, a subset of those strings belong to the, I mean a subset of those strings are the yes instances of this language, and some other subset, some other disjoint subset are the no instances. Okay. It is not that the complement of the yes instances are the no instances necessarily. So, the yes instances, yes. So, I mean this is just another way of writing whatever let us say define. So, when we define let us say BPP. Okay. So, if we look at the class C to be our class P, then BP dot C is sorry BP dot P is nothing but the class BPP. Okay. So, how did we define BPP? So, we say that given, so we said that a language L is in BPP. Okay. If for all x, x belongs to L implies that the probability of acceptance is greater than 2/3, or in the case of strong BPP it is greater than 1 minus 2 to the power minus q n, and if x does not belong to L, then the probability of acceptance is less than 2 to the power minus q n. Okay. So, this is how we defined it. So, but what about other things? So, basically this has the promise that every string would either have this property or it would have this property. So, that is how this thing is defined. So, this is what is known as a semantic based class as opposed to syntactic class. So, what is happening here is that so I am just not telling you that the complement of the yes instances are the no instances. I am enforcing that if something has to be no, it has to satisfy some property, and that has to happen for every string. So, every string must necessarily have either this property or this property. Okay. So, that why pi is not a complement of pi? No, it is a complement. So, here it is a complement, but it is not a complement based on the property of the machine. Okay. So, I am not saying that for all x I will accept x if x has this property and otherwise I will reject x. Okay. So, it is not getting rejected based on the property of that machine, it is basically getting rejected by an extra stronger property. So, every string, yes, every string either belongs to this set or belongs to this set, but there is something more strong that is there in the definition of that language. Is sigma star. Okay, so this is true for all x actually, yeah. So, maybe I should write it here that pi y intersect pi, and of course, that follows from the definition, but this is more important. So, this is equal to 0 1 star in this case. So, it has to happen that either of these two inequalities are satisfied. Okay. The promise is in the machine. I mean, the machine has this property that it will either accept it with very large probability, or it will accept it with very small probability. It will not have something in between. So, that is the promise in it. Okay. So, the first part is basically what we will focus on today, and this basically uses in some sense an extension of the Valiant-Vazirani theorem that we proved. So, let us see how we will prove this. So, what I will prove is, we will prove two lemmas. Okay, so I have theorem 1 and 2. So, let me call this lemma 3 and lemma 4. So, lemma 3 states that BP dot parity P is the same as BP dot parity dot BP dot parity dot P. Okay. So, no matter how many such pairings you have, it basically boils down to just one pair, and lemma 4 will prove that there exists C is contained in BP dot parity dot C. Okay, so, if you have a there exists quantifier, it can be replaced with a BP dot parity quantifier, okay. And this basically follows from Vaillant-Vazirani, I mean, as we will see maybe next class. So, now suppose we have these two lemmas, can we prove theorem 1? Okay. So, let us see proof of theorem 1 based on these two lemmas. So, what is pH? So, I can just say that, so let us consider, okay. So, we will prove this by induction. So, we will show that for all k, sigma k p is contained in BP dot parity dot p. Okay. So, when k is equal to 0, this is nothing but the class P. Okay. So, that trivially is in the class BP dot parity dot p. Suppose sigma k minus 1 p is contained in BP dot parity dot p. Okay. So, then what can we say about sigma k? So, what is sigma k? So, it is there exists pi k minus 1 p. Okay. Okay. Yeah, we can do that also, but actually the property that we will use here is that this BP operator is closed under complement. Okay. I mean, I can always flip the answer in the end, because so yeah, so it's not, I think I need to give a formal proof of that. Okay. So, if I just apply this lemma here, what I have is this is contained in BP dot parity dot pi k minus 1. Yeah, we can again apply, actually, yeah. So, we can do that again actually, but pi k minus 1, no, actually there is a problem. So, pi k minus 1 is for all sigma k minus 2, but here I am only stating this for there exists C. Okay. So, the property that is used here is that this is closed under complement. I mean, if sigma k minus 1 is in BP dot parity p, then pi k minus 1 is also in BP dot parity p. Okay. We cannot, because we are only stating this lemma for there exist. So, pi k minus 1 is for all C, but actually it does not matter. I mean, basically since it is closed under complement, we can also have a for all version, but okay. So, let me just mention it here, and maybe we will look at the proof next time, that this implies that pi k minus 1 is also contained in BP dot parity dot p. So, now I can just write this as BP dot parity dot BP dot parity dot p, and by lemma 3 what we have is this is contained in Bp dot parity dot P. Okay. So, that proves theorem 1 for us. So, the point is how do we prove lemma 3 and lemma 4. So, again let me just give so lemma 3 needs certain non-trivial steps. So, let me just give the steps today and we will look at the proof tomorrow. So, I will just call it claim 5. Okay. So, the first claim is that parity of any complexity class C is equal to parity dot C. Similarly, Bp dot C is equal to Bp dot C, and finally, Bp dot parity dot C is equal to parity dot Bp dot C. Okay. So, suppose if we have these 3 claims, then lemma 3 follows quite easily. See, one direction is trivial, I mean the left hand side is contained in the right hand side trivially. What we want to show is that Bp dot parity dot Bp dot parity dot P is contained in the left hand side. So, by let us say claim 7, I can switch these 2 quantifiers. Okay. So, this gives us Bp dot Bp dot parity dot P. Okay. So, this is by claim 7, and now I use claim 5 and 6 to get the following. This means that Bp dot parity dot P by 5 and 6. Okay. So, that is at least the first component for us, provided that we have these 3 claims. Okay. And again these 3 claims are not difficult, I mean you can just try out maybe the first 2 are quite trivial, third one is some little bit of work, but we will look at that next time. Huh? Third one? No, it is not difficult, I mean it is just again by probabilistic argument. I mean you probabilistically argue that there will be some good certificate with high probability. Okay. So, when we will so basically the difficult part of these proofs is writing out the definitions and properly deducing the next step. Okay. I mean there is no nothing magic happening here, but the next lemma, so lemma 4 is more non trivial, but since we have already proved Weyl and Vazirani, so we will see that it is actually a an extension of Vaillant and Vazirani. So, we will be able to do that maybe tomorrow, and theorem 2 is again, so it uses some other ideas. Okay. Okay, so we will stop here today.